So after Mars and the Moon, we move towards the Sun, and we go to Venus. So the speaker is Giulia Maia. Giulia Maia did her PhD with Margrethe Zorek in the Observatory of Côte d'Azur. Then she had a long postdoc in the DLR, the German Space Agency in Berlin, and now she just got a position as a scientist of the European Space Agency in Madrid. So, Giulia.
Thank you very much. It's a pleasure to be here to talk about Venus, and in particular seismology on Venus. But as a caveat, I'm not a seismologist. But the important thing is there's also no seismic data for Venus, so it's all going to be good. I'm just going to talk about what we think it could be, the signals or the amplitudes and the seismology of Venus, and how we could potentially detect those, and most importantly, why we think a mission detecting quakes on Venus is a crucial next step for our understanding of the dynamics of terrestrial planets in general, and more specifically big terrestrial planets like Venus. Okay. So we've seen this image a few times already in different forms, but this is all the planets on the visible spectrum, and showing some key properties here. And the first thing we can see is, of course, that Venus and the Earth, they are very similar in terms of size, but also in terms of mass, and particularly the bulk density is almost the same. So it seems like they're made about the same stuff. Venus is a little bit closer to the Sun, of course. And I think another important property that we can see here is that Venus is basically the only planet we cannot see the surface at all when we look at it in the visible. And this has been a problem for decades or centuries, because until we had radar technology and space exploration, we basically didn't know anything about what was going on there. And many people actually thought that it was really Earth-like, with kind of a little bit warm swamps, tropical, with dinosaurs and things like that, like actual scientists saying these things on the early 20th century. But as we got more technology and more data, we found out that this is not really the case. And when with radar, we managed to actually see the surface of Venus. So this is a synthetic aperture radar global mosaic, where we have, like, when we have bright, this is a highly tectonized, very rough surface, and dark is more smooth terrain. And then we looked at Venus in detail, and we saw that actually Venus and the Earth are not really that similar. So we found out that actually the temperature of the surface, because it has a super thick CO2-dominated atmosphere, is 470 degrees. Also, because of the atmosphere we have at the surface, 92 bars of surface pressure, we did not detect any dynamo or any magnetic signature from the crust on Venus, maybe because we haven't measured it well, but that's another topic. And less and most importantly, Venus does not have plate tectonics like the Earth. So although these two planets, they seem very similar from a bulk perspective, they are in fact quite different from a geological and geophysical perspective. This is a map of the topography of Venus. This is one of these on radar very bright tectonized terrains that actually are highlands. But Venus overall, the topography is very smooth and flat, and with these punctual highlands. So this one is one of the biggest ones. It's about the size of Australia. Yes. So this is just to show a little bit like the smooth basaltic plains. They have a lot of wrinkle ridges and tectonic structures. But then when we go to the highlands, we have two main types. We have these what we call crustal plateaus of tessera plateaus, which from gravity data analysis we know are very likely close to isostatically compensated. And there are also some recent indications that they might have a felsic composition. So this is showing that potentially Venus have continental-like structures, which could indicate that it had water in the past. But this is still very early on, and we still don't even know if these are actually felsic rocks. But yeah, it's a very big deal and a actually big topic for next missions to the planet. On the other hand, we have highlands that are volcanically dominated, so they have They have plenty of volcanoes on it, and they have these very large gravity anomalies, which indicate that they are actually dynamically compensated. So they don't have these roots like the plateaus, but they have this, they are buoyantly compensated by, for example, a mantle plume. And we think these are actually similar to hotspots on the Earth. And there are about, debatably, between 5 and 10 of these features. All right, so as I said, we have these hotspots, and you know, and these are a map of the bigger volcanoes on Venus. In total, there are over 80,000 volcanoes mapped, but most of them are very small and clustered on these, what we call shield fields that are on the lowlands. But on this this volcanic highlands, we have actually the very large volcanoes that concentrate there. So these are three of these highlands, and they're actually connected by very large, tens of thousands of kilometer rift systems. Another very important structure on Venus are the coronae. So the corona, they are like this circular structure. This is the biggest one, called Artemis. These are 2,000 kilometers big, and they have this rim. And the biggest one of them, actually, especially Artemis, we think that they could be, and this is some work by Andavai, that indicates that they could have been formed via subduction events. So peeled back, you have a plume, and then this causes some peeled back subduction, and it could be the only terrestrial planets that we actually have ongoing subduction. And sometimes this corona as well are part of the rifts, and they form this chain. So these are very unique features to Venus, and we think they are mostly associated with small upwellings of mantle plumes, or sometimes this larger one may be a special case by a big plume and subduction. Just a quick note about what we know about the surface composition. So Venus doesn't have a lot of data about the composition of the surface because it's very, for example, difficult to do spectral analysis from orbit. But we did have some landers that went there from the Soviet era that show that the surface composition is very similar to mid-ocean ridge basalts on the Earth. And this is just to show one of the few pictures we have from the surface from one of these landers. Okay. Now, I think one of the key observations of Venus, once we had this global map of the planet, was the crater distribution. So Venus, if you're a planetary scientist, you know that the way that we date the surface is through crater counting. So on the moon, for example, we know that the mare, okay, now we have direct measurements, but the mare have much less craters, so they are much younger than their notocyte terrains and so on. On Venus, first of all, we don't see any clear clustering, like any clear older terrain than the other. The surface seems to be all about the same age. And also, there are very few craters, something between 900 and 1,000. And there's no big, massive basin as we have in the other terrestrial planets. And this shows that actually the surface of Venus is quite young. It's about 250 million years old. This is, in planetary science, this is quite young. And it shows that the planet is probably more active geologically than the smaller counterparts. Yeah, very few craters, these are a few examples. They are modified, so they have been through some kind of modification via tectonism or volcanism. This is one of my favorite examples of one that has been modified by tectonics. But all of these observations led to a very strong belief that Venus went through what we call a catastrophic resurfacing event. So there are two main hypotheses on why Venus has this crater distribution, and this one dominated for most of the past 30 years. That Venus actually about 250 or 500 million years ago went through a major geological event, for example, a major plate tectonics events that completely subducted the entire surface and created a clean slate for new craters to appear. And this, in this scenario, Venus today would be basically quite dead geologically. It would be, it had this event, and then everything kind of stopped, and Venus would be today in a geologically quiescent state. But there has been some new ideas that, in fact, it might not be necessary to have this catastrophic event to explain the distribution of craters, and you could have something called equilibrium resurfacing, where stochastic creation and removal of craters leads to finally this same type of distribution. So it could be something much more mild, and via volcanism or tectonic activity, you could lead to this distribution as well. And I think this is one of the main debates that we have on Venus today. And actually, these two resurfacing hypotheses lead to two different views of what is the current geodynamic regime of Venus. So we know it's not plate tectonics, but what is it? So from this catastrophic resurfacing idea, there are two main scenarios that we can think of. One is that Venus was actually some kind of mobile lid, which is, let's say, a big class of plate tectonics. So we have this lithosphere that was being subducted and created and so on for most of this evolution, and then at some point, something changed. Maybe some kind of volcanic event that completely changed the surface conditions, for example, that led to the elevation of the temperature, and this elevation of the temperature could have led to the stop of plate tectonics and leading the planet to what we see today. And the other view on this side is what we call the episodic lid regime, in which we have a cycle between a planet that is quite quiet and a simple stagnant lid, not much going on the surface. And because it's a big planet and you start building and heating up the planet interior a lot, at some point you create some kind of, you lead to this super hot interiors that leads to this huge breakup and catastrophic subduction event. And then this cools down the planet and everything starts again. And then the idea would be that you had one of these big catastrophic resurfacing about 500 million years ago, and now today you have this kind of quiet stage again. And then we have the equilibrium resurfacing, in which, of course, we don't have plate tectonics today, but there are other ideas on how you can have this kind of continuous resurfacing of the planet. And these are two other types of scenarios. So we have heat piping, in which this is what we know is for the moon Io, that you have a lot of volcanism. So you just have volcanoes and volcanoes and volcanoes that are just reshaping the planet and destroying the craters and so on. And then we have another idea that is more recent called plutonic squish lid, that instead of having volcanic dominated geodynamics, you have intrusive magmatism dominated tectonic regime. And in this case, when you start having a lot of intrusions, what happens is that you weaken the lithosphere, and this allows for local or regional dripping and delamination of the lithosphere. And you have, instead of having this global set of plate tectonics like on the Earth, you have this small scale, sometimes patchy recycling events that can also lead to what we see today. So these are all the scenarios that we have, and we still don't know what's going on. Okay. So one key question to answer this is, how active is actually Venus at present day? Because if the planet is indeed in this quiet stage where we just went through this event, and today the planet is basically not even convecting much today, then we wouldn't expect to have a lot of geological activity on the surface. The fact is, we don't really know what is geological activity of Venus, but there has been recent observations, not recent observations by Venus Express in the 2010s, and also reanalysis of old data from the 90s that show that Venus might be more active than we thought. So first, there's these observations from the atmospheres that show that the SO2 abundances at 70 kilometers altitude varies with time. And one of the propositions for this is caused because of outgassing of volcanoes. there was also these observations that show that, also by Venus Express, that some volcanoes on Venus, they have a different 1 micron emission signature. So they have this high emissivity anomaly, which was interpreted as unweathered basalt. So this would be indicate also very recent volcanisms of, there's still a lot to do with weathering experiments, but this could mean from years long to hundreds of thousands of years old volcanic flows. And finally, I think this is probably the strongest evidence we had until now. It was the detailed analysis of radar data from this mission from the 1990s by NASA called Magellan that shows that, in fact, by 2 different cycles of the mission that was apart, 2 years apart, you had this change in a volcanic vent and potentially a new flow, but this is harder to tell, which would indeed indicate active volcanism on the planet today. So this is all pointing towards Venus is probably geologically active today, but how active, and can we use this to distinguish between these geodynamic scenarios? And because we have all these big questions, actually, in 2021, 3 missions to Venus were selected, and two orbital missions that are focused on doing new imaging of the planet. So this is NASA mission, ESA mission, NASA mission. This one is a probe that will measure the atmosphere, so I won't focus on these. But these 2 is going to give much higher resolution radar data, topography, gravity. Envision, the European one, also going to assess, measure a lot of the atmosphere. And Veritas actually is going to have the capability of doing repeat pass interferometry to actually look for centimeter scale changes on volcanoes. So that's going to be very exciting, but it's going to be very around like 10 to 20 spots that we're going to be able to look at that. So it's going to give us a picture on potential activity, but it won't give us, I doubt that it's really going to give us the full picture of how active Venus is today. And of course, what we know from the Earth and also what we learn from InSight and the Moon is really to have this assessment of, like a more global assessment of tectonic activity and geodynamic processes, and also to properly constrain the interior of the planet. Seismology is extremely important. So we think that having a seismological mission to Venus is a key next step to understanding the geodynamics and also the tectonic processes on Venus and better constraining its interior structure that is very poorly known. But at the same time, we need, when you plan a space mission, it's a bit complicated because you have to answer a question, but you also have to say what you think you will get before, so they don't send this mission and you don't find anything. So you have to do some studies to try to figure out, okay, what we expect to find, and can we detect them with what instruments, and so on, because it's such a huge investment as we were seeing in the previous mission. So what we had put some effort in the past years with the EC team, but effort is actually growing, I think, all over the world, is trying to understand what we expect for Venus in terms of seismicity and what would be the best way to detect these seismic waves. So the first question is Venus a seismically active planet? So we saw there is probably some volcanic activity going on. The surface is clearly very highly tectonized with corona rifts, these features that were formed by probably some sort of shortening, not continental collision, but some strong compressive tectonics. So there's a lot that at least was going on at least some 100 million years ago, maybe, hopefully, until today. But we don't know. But another key question on Venus is how deep can quakes on Venus be? Because Venus, the surface is very hot, and as you all probably know, to have brittle deformation, to have quakes going on, you need to have, this is very closely related to temperature. And so there are even people that say that Venus have a negligible brittle layer, and probably there are no quakes there. So what we wanted to do is to assess really with data and models what would be the thickness of the seismogenic layer on Venus. And also, in the second step, how many quakes and how large could quakes on Venus be, and which instruments we would need to detect them. So this first analysis that we did was to try to figure out what could be the seismogenic thickness, as I said, and to do that, of course, since we don't know anything, we went to what we know on the Earth. And on the Earth, we know that there's this very clear correlation between temperature and depth and maximum depth of the quakes. And there's this, let's say, kind of classic limit of the 600 degrees Celsius. And there's also some experimental studies that show that this value, something between 500 and 600, is also what we expect for the brittle deformation of basalt. So we thought that this was a good first-order proxy to start looking at what would be the seismogenic thickness of Venus. So to do that, we have to have constraints of the thermal structure of the lithosphere, and then we can estimate what is the depth of this layer. Okay. So the first part of the analysis that we did was to put together all the elastic thickness estimates that were done for Venus. So basically, when you have a load from a volcano or a corona or any surface feature, this is going to deform the surface, deflect the surface, and the amount of deflection is associated with what we call the thickness of the elastic shell. And this is actually closely correlated with the temperature of the lithosphere. And by assuming some rheologic properties and strain rate, we can actually get the lithospheric thermogradient from that. So what we did was to gather from several different studies these estimates, elastic estimates, make some assumptions on strain rate and rheology, get the thermogradients, and then get what would be the depth of the 600 degrees Celsius depth. And that's what we end up with. So we have, in some regions, very thin seismogenic layers, and this is typically related to what we think maybe active corona are, and some regions that can reach up over 30 kilometers. Of course, there are very large uncertainties here, but on the map, I cannot show this very well, but of course, there are uncertainties there. Then we went to the second step, which is to see what geodynamic models tell us. And this was done with a geodynamic model developed at the DLR, where I did my postdoc. We did a 3D models of the full 4.5 billion years evolution of Venus. This is a finite volume code, and with core cooling and also a radiogenic decay of the mantle. We have Arrhenius loss for the viscosity, depth and temperature, viscosity, thermoexpansivity, thermoconductivity. And one key thing that we considered was the melting processes and melt extraction. So every time the temperature of the mantle goes beyond the solidus, we melt, and then we can actually place this melt either on the surface as extrusive magmatism, or also within the subsurface, or let's say around the base of the crust, as intrusive magmatism. And what we did was to do kind of two end-member scenarios here, one where we consider that all the melt generated are placed extrusively at the surface, and one in which the majority of the melt, 80% of the melt, is actually placed intrusively, and this is close to this platonic squishy lid scenario. And we ended up with two kind of maps of seismogenic thickness. When we consider fully extrusive volcanism, we actually end up, because we put this melt on the top and it cools to the surface temperature immediately, and you put more and more and more and push down this layer, you end up with a super thick and cold lithosphere that is actually not what we really see for Venus, and also a very deep seismogenic layer as well. While when we have a lot of intrusions, what this leads to is that you have these delaminations of the lithosphere, and also the heating up by the intrusions themselves that cools conductively, and you end up with a much thinner and warmer lithosphere. And when you actually compare the observations of these two kind of end-member cases, you manage to match much better. It makes much more sense to have this highly intrusive case. So this is another way we can kind of rule out this heat pipe scenario for Venus, where you have only all the melt produced is extrusively put on the surface. This would also generate an extremely thick crust that is also not what we expect. So it's another thing to rule out heat pipe. But it shows that plutonic crucially is something that works well until now. It works well with the observations. Okay, so we put together these two kind of sets of constraints to give an overall estimate of the seismogenic thickness, and we see that it can vary between 2.5 and about 40 kilometers, with a median value of 22 kilometers. And we have that when we have these intrusions, like the places where we have these intrusions in the models, is actually you can really heat up the lithosphere locally on these places and reach thermogradient values that are 20, 30 Kelvin per kilometer that really match what we see for some corona and things like that. So it's a way to explain why in some places on Venus we have such high thermogradients and thin seismogenic thickness. But overall, we would think that there is a brittle layer on Venus, and we could have quakes there. So in the second step, we did, actually this was said by Ines von Zelst, and we tried to, and this is really like order 0 estimates of seismicity on Venus, but to try to find analogous between Earth and Venus tectonic settings. And so here what we did was to get the CMT catalog of earthquakes. We put that on some studies that defined tectonic settings for the planet, and we subset these quakes according to these tectonic settings. And then we start comparing what could be potential analogous between Earth and Venus. For example, for continental rifts, we can say that this could be the same level of seismicity as the rifts that we see on Venus. Where we have continental collision, it could be where we have this large-scale mountain. So this is the largest mountain range on Venus that is clearly formed by compressive tectonics. And we start playing this game and doing this estimates to see what we could expect for Venus. But just to show you, so this is how the distribution of quakes looks like. Of course, completely dominated by subduction zones. And this is the other kind of types of tectonic settings. Then from this, we actually get number of quakes per year per kilometer squared that actually allow us to apply this directly to types of features on Venus. All right, and this is what we end up with. So we have 3 scenarios. Okay, so this is estimates of moment magnitude for the Moon, for Mars, and here's kind of 3 scenarios that we consider for Venus. And this line here is kind of the reference for the Earth. On this gray one here, we assume that Venus is entirely, only has tectonic seismicity similar to intraplate seismicity on the Earth. So this would still be above what we have for Mars, but of course, this is what we consider to be our lower bounds, kind of a stagnant lid Venus scenario. Then we had a scenario in which Venus is more active. So we have this proportion, this correlation between Venus rifts and here mid-ocean ridges. So we did one test with mid-ocean ridges and one with Earth rifts, continental rifts, fault belts with continental collisions, and we assume that 30% of corona correspond to subduction zone, which I think is too much. But yeah, we do think that the bigger ones are indeed could be active subduction zones. So that's what we assumed here. And then we went to extreme Venus, which is what is the maximum you can expect. And in this case, we assume that all corona are subduction zones, which is insane, but it's just really to give the absolute maximum upper limit of what could be seismicity on Venus, which should be comparable to the Earth in this case. yeah, and so these were the main results of this paper. And so the next thing we needed to do is to compare this with options of observation, seismic observation techniques or instruments that we could have on Venus. And that's the last part of my talk, which I think Philippe or Rafael should be giving, but here I am. So I'll do my best. But we have big experts on that here. So we considered 3 scenarios, and this was a study led by Rafael Garcia. And first we consider lander seismometers, as we have done for Mars, the Moon, and the Earth. The problem is that on Venus, we don't have the technology to have a lander that survives at high temperatures for more than hours or more than a day. So, and to detect quakes, you need time. So this is a huge constraint for lander seismometers. And until we don't have this heat technology that survives, computers that survive at 500 degrees Celsius, it's very hard to have any lander seismometers on Venus, unless you do active seismics or something like that. So actually, the most interesting way promising way to detect quakes on Venus is with the atmosphere, because when you have an earthquake, you have these surface waves, Rayleigh waves that are very well coupled with the atmosphere, and they're going to perturb the atmosphere. And you can indeed detect those on the Earth. We have shown that, and I'm going to go into that in a bit. Detect those with sensors on a balloon or even from orbit. And so, because on the atmosphere of Venus, on the cloud deck, you have temperatures that are very mild around Earth temperatures, it is a way to have longer-term missions, and of course, with orbiters, you can survive for years. Okay, so seismology from balloons. Where are we now? I think one key result that is actually quite recent, also led by Rafael Garcia, was the first detection of a quake with pressure sensors in 4 balloons. So this was a CNES project, and they detected this magnitude 7 earthquake at Flores Sea. And this was a very, very interesting result, was a first detection. And more recently, actually last year, Marouche and others, she's also here, they showed that with these 4 balloons, you can actually, only with this data, you can invert for the location of the quake and also the interior structure of the planet reasonably well. So this is very promising to show that we can do proper nice science with only balloon seismology. The next step is from orbit. So this is, while the wave propagates through the atmosphere, actually because the density of the atmosphere is decreased, you actually start having bigger amplitude waves, and this shows also has very good drawing skills. And so, in fact, at the upper atmosphere, around 70 to 80 kilometers, you have these air glow layers, which is kind of a chemoluminescence processes that work for example, OH or sodium, and at different wavelengths at different altitudes for different elements. And these air glow layers, actually, when you have this propagation of the waves through the atmosphere, they're going to get disturbed, and this can actually be detected. So if you have an imager, you could potentially detect the earthquake just by measuring the air glow layer. And this is super cool. Unfortunately, we haven't done that yet for earthquakes, but there are these very impressive results from at tsunami. This was from the 9.9 magnitude Tohoku earthquake that led to the tsunami, and this is the tsunami front, and these are the ripples that you see in air glow, which I find really, really cool. And I would say that we are on the way to detecting this for actual earthquakes, Rayleigh waves, but it has not been done yet. I think, but there are people putting efforts on building these instruments to have this detection, and this would be very strong to push for such observations in other planets as well. So this is kind of the main result from Hafez's work, which showed, so these are, again, the three moment magnitudes estimates for these three scenarios on Venus, kind of stagnant lid, mildly active, and super active. And these are these three different sensors that I mentioned. So here is for a lander seismometer that would survive 12 hours on the surface. And on this case, we would only detect any quakes if we had really Venus being as active as the Earth. So it's very, yeah, I'd say it's a very risky, it would be a very risky mission with such mission duration, right? So we need this better technology to have a lander that survives for longer. Then we have the balloons that can survive for, in this case, we assume that it would survive for 3 months. And this is based on previous mission concept proposals. And it gets better. You can detect now, because it survives longer, you can detect this larger, probably could detect large quakes if over magnitude 6 if Venus is, let's say, somewhat active. But I would say that at this point, because of the length of how long an orbital mission can be, the most promising type of observation, type of instrument that we could put on Venus, orbiting Venus to detect quakes would be these air glow imagers. But there's a debate on how much groundwork we still need to do to get there, because we have not detected that yet for the Earth, and maybe we do need that before going to Venus, or maybe not, because Venus, the atmosphere is so thick that we think it's 2 orders of magnitude better coupling between the surface and the atmosphere for Venus and for the Earth. So it's probably more likely to have the signatures on Venus than for the Earth. But yeah, for now we still have to do some work on that. We did propose a mission, but it was not selected this time. So to conclude, yeah, so Venus' harsh surface conditions makes it very difficult to have a lander like we had for InSight or the Moon. But we think that with atmosphere, in the atmosphere is kind of the answer to have start understanding what is Venus seismology, what is its current tectonic levels, and better constraining its interior structure. And this is really a key next step for Venus science, but also for planetary science in general, to put Venus on the scope of the terrestrial planets and understanding what is its interior, and also better constraining what could be its tectonic regime and what are the planet's heat loss mechanisms today. And of course, having such an Earth-like planet so near to us, but with the same density as the Earth and the same size, but without plate tectonics, and for reasons that are still not very clear, shows us that, in fact, understanding the geodynamics of this planet and understanding its interior properties, geophysical properties, and rheological properties as well, is key to figuring out what are the preconditions and criteria to, in fact, have a planet with plate tectonics like the Earth. Thank you very much.